Myself, Dr. K. Viswanath Allamraju, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. In this session, we are going to study bending stresses in unsymmetrical sections. What is symmetrical section and what is unsymmetrical section? We are going to study in this. Now here, the course outcome related to this topic is number 4, course outcome CO4. And it is, apply the knowledge of theories of failure, shear force and bending moment relations for analyzing the flexural stress, shear stress distributions and failure of beam sections. And the level of Bloom's taxonomy here it is related to apply level. Now here, what is a symmetrical section? And symmetrical sections are here. There are different sections mentioned here. One is rectangular, another one is I section and channel section, that is C channel, and also T section. Among these 4 sections, there are 2 sections, that is rectangular section is symmetrical about both x-axis and it is y-axis. And where about next I section is also here. The way I section is, this I section is symmetrical. I section consists of one web and 2 flanges, and the top flange and bottom flange both are equal in length, both are equal in geometry. That's why it is symmetrical about both I, X and Y sections. Here rectangular section is symmetrical about both X and Y sections, both X axis and Y axis. And one more thing, I section also symmetrical about both x-axis and y-axis. Now the remaining 2 sections, that is channel section and T section, are here. The channel section is symmetrical about x-axis. Channel section is symmetrical about x-axis, and it is unsymmetrical about y-axis. Unsymmetrical about y-axis. And whereas T section, the T section is symmetrical about y-axis, is symmetrical about y-axis, symmetrical about y-axis, and unsymmetrical about axis X, and unsymmetrical about x-axis. Now this symmetry means, if you observe a rectangular section is symmetrical about both x-axis and y-axis. How here it is? If we consider it is about x-axis, if you fold this geometry, this plane about x-axis, then equal geometry will be there on both the sides. So then that means it is symmetrical about x-axis. The dimension about top side and the bottom both are equal. both length and width are both having equal shape. That is exactly meaning. That means it is symmetrical about x-axis. Now, if you fold this plane about y-axis vertically, if you plane about y-axis, if you fold, then the shape, the geometry on left side and right side is in same shape and also size. That means it is symmetrical about y-axis. Now here the rectangle is a very good design. I mean very good plane, that is so useful plane, such a way that it is symmetrical about both x and y-axis. And rectangular, here it is one more square. If you consider the square, also the unique property of the square, it is also symmetrical about x-axis and y-axis. And if you consider the circle, the geometry of the circle, it is also symmetrical about exactly circle. If you consider, it is also symmetrical about both x and y axis. That is the uniqueness of these planes. Now if you consider another section, this I section, consider the I section. In this I section, if you fold again about x-axis, the top and the bottom portions are having equal shape and size. That means it is symmetrical about axis x. And if you fold about y-axis, if you cut the section, if you cut the shape, both the left side and right side having equal shape and equal size and dimensions. That means that's why it is symmetrical about both x and y axis. That's why these two rectangular and I sections are having double symmetry. And here, if we consider this channel section, the channel section is symmetrical about x-axis, that is neutral axis or centroidal axis, but not about y. So it is symmetrical about, that's why it is a single symmetry. Whereas the T-section geometry is such a way that it is symmetry about y-axis. And what about x-axis? It is unsymmetrical about x-axis. So this is the concept about symmetrical section. Now coming to unsymmetrical sections. If we consider the unsymmetrical sections of this is the section. In this section, the center of, if you fold about a neutral axis, both x and y, about x-axis, it is unsymmetrical. This geometry is top is different, is non-different from bottom one. So it is unsymmetrical about x-axis. And it is symmetrical about one thing. Symmetrical about which axis? Y-axis. It is symmetrical about axis y. Now, even though, suppose, if we extend the length more, then it is unsymmetrical about both x and y axis. X and y, it is unsymmetrical. Unsymmetrical section. Then it is called pure unsymmetrical section. Both x and y axis, it is, suppose, as I told you, extended little bit at the top of the flange. Now here one more sections are mentioned, the T section and inverse U section and also the section of I. Now these are the neutral axis. About this neutral axis, about x-axis, it is unsymmetry. It is also unsymmetry figure 2 and figure 3 also unsymmetry. So these are unsymmetrical sections about x-axis. If we consider about y-axis, these are all symmetrical sections about y-axis. Why we consider unsymmetrical sections about x-axis sections? Because in solving the bending stresses, we need bar y and moment of inertia I. These values we considered about neutral axis parallel to axis x. Parallel to axis x we consider. That's why these are unsymmetrical sections about x-axis. This is the concept here. So these are the various sections. Now we are going to solve what is the variation of bending stress on unsymmetrical sections about x-axis or about neutral axis parallel to x-axis. Alright. Now let us solve the problem. A cast iron bracket is subjected to bending, has the cross section of I per with unequal flanges. These are the flange 1, top flange and bottom flange. The dimensions of the section are shown in figure. Find the position of the neutral axis. First we have to find the position of the neutral axis and the moment of inertia of the section about the neutral axis. And that is called bar y. Find the position of the neutral axis, y bar. And if the maximum bending moment on the section is 40 meganewton millimeter, that is 40 into 10 power 6 Newton millimeter. Determine the maximum bending stress. And what is the nature of the stress? What is the nature of the stress? So how many objectives we have to find out here? It is first, position of the neutral axis. Second one, the moment of inertia about the neutral axis. And the third one is the bending stress. And the fourth one is the nature of the stress. Nature of the stress. Nature of the stress. These are the four objectives we have to calculate in this problem. Now, we already mentioned here, it is shown in figure. They did not mention what type of beam it is. So they are shown in figure. From this figure we can understand that it is a cantilever beam having a section of I section which is shown in figure, and it is unsymmetrical section. It is unsymmetry about x-axis and it is symmetry about y-axis. For such type of sections, how to calculate the variation of bending stress along the cross section. Now, how to find out the bending stress? And first we have to find out the position of the neutral axis. So what is it meaning? The position of the neutral axis means the value of centroid. What is the centroid? Bar y in vertical with respect to from the base axis. So before that we have to make it different sections. It is section 1 and it is area 2 and it is 3. Or you can consider according to this is A1 and it is A2 and A3. Now what is the area of this section 1? That is, it is a rectangle 200 millimeter times 50 millimeter. So bar y, the y bar formula for y bar here, it is A1 y1 plus A2 y2 by A2 y2 plus A3 y3 by A1 plus A2 plus A3. Alright. Here A1 means area of section 1, area of the flange 1 and flange 2 and web. Now here A1 y1 is the distance from reference axis x to the centroidal position of this position. This is the distance y1. What is y2? If we consider the section 2 and it is section 3, the centroidal distance, this is y2. And what is y3? Here it is, this is the y3. So y3 equal to 50 by 2 and y2 equal to 50 plus 200 by 2. It depends on the section. You can consider from the bottom section is 1 and top section is 2, like that. Now let us begin. So here we considered in this problem, based on the solution, we understood that it is the bottom flange A1, bottom flange, and A2 and A3 is the area of the top flange. Bottom flange and top flange. The area of the bottom flange here, that is 130 times 50. It is rectangle area, that is 6500 millimeters square. The formula of it is the section is symmetrical about y-axis. Yes, so we have to calculate the bar y. That's why here a1 y1 plus a2 y2 plus a3 y3 by a1 plus a2 plus a3. That is a1. What is the y1? Distance of centroid of a1 from bottom face, from bottom axis. This is the x-axis. So that is 50 by 2. That is 25 millimeters. Next, A2 means area of the web. The area of the web is width is 50 millimeters and length is 200 millimeters. So area of the web, that is 200 times 50, that is 10,000 square millimeter. Now y2 is the distance of centroid of A2 from bottom axis. So this is the centroid of this is y2. That means 50 plus 200 by 2. That is 150 millimeter. Next, what is y3? This is the y3. That y3 means 50 plus 200 plus 50 by 2. 50 plus 200 plus 50 by 2. That is 275 millimeter. That is y3. Distance of centroid of A3 from bottom face. Now, what is the A3? Area of the top flange. The area of the top flange is 200 times 50. That is 10,000 square millimeter. Substitute all these values A1, Y1, A2, Y2 and A3, Y3 in the formula of bar Y, that is A1, Y1 plus A2, Y2 plus A3, Y3 by A1 plus A2 plus A3. Then we can calculate the distance of neutral axis, that is the location of the neutral axis. After substitution, the bar Y value is 166.51 millimeter. This is 166.51 millimeters. So the neutral axis is at a distance of 166.51 millimeters from the bottom face. That is the first objective. The first objective was achieved. That is 166.51. This is the neutral axis. Now it is the bar Y from base. Now we want the distance of the top face. What is the distance? Total distance is how much? 50 plus 200 plus 50, 300 millimeters. So 300 millimeters minus 166.51, then we can obtain the top layer distance. That is the Y maximum distance. That is 300 minus 166.51. Now, what is the second objective? The second objective, moment of inertia of the section about neutral axis. So, there are here three areas are there. There is the bottom flange, web and top flange. So, the moment of inertia of this section about neutral axis, that equal to I1 plus I2 plus I3. So, I1 means moment of inertia of bottom flange about neutral axis. This is the neutral axis about bottom face, about neutral axis. All will consider from neutral axis. So that means, that is according to parallel axis theorem, I1 equal to IG x1 plus a1 into bar y minus y1 whole square. This is the formula. So here igx1 plus a1. What is igx1? That is bdq by 12. This is the section 1. What is the b? The b here it is 50 b cube. The b is the 130 and 50 cube by 12. Next area, that is 130 into 50, that is 6500. What is bar y minus y1? Here it is bar y is 166.51 minus y1, that is 50 by 2. Then the distance comes. The value of that I1 is 1315171, 86.6 millimeter per 4. Similarly, we have to calculate I2 and I3. What is that I2? Moment of inertia of web about neutral axis. So again, formula for this I2 equal to igx2 plus a2 times bar y minus y2 whole square. The distance. The distance of central distance of web and about neutral axis. That is the meaning this term. Now how it comes? We know the bar y and we want this distance. How it come? If you subtract this distance, then it will come out. So now how it is? BD cube by 12. What is it here? 50 into 200 cube by 12 plus A2 50 into 200 minus times 166.51 minus 150 square. This is the value of I2. And whatever next I3, same concept. igx2 plus a3 times bar y minus y3 whole square. That is igx3. This is 200 into 50 cube by 12 plus a3 200 into 15 times bar y3 minus, that is 275 minus 166.51 whole square. So the value of that I3 here, it is 119784,134.3 millimeter per 4. The sum of moment of inertia I1 and I2 and I3, that is the total sum, that is 284907234.9 millimeter per 4. That is I value. Now this is the moment of inertia. That is the second objective. Next, now the distance from the upper fiber, this bottom fiber is 166.51. That means total distance is 300. 300 minus 166.51, then the top layer comes, that is 133.49 millimeter. And whatever bottom fiber, the bottom fiber is 166.51 millimeters. Now, which value we have to consider? We have to consider the maximum value. That is what y maximum is. Now, the maximum value, that is about, in comparison with among these two values, 133.49 and 166.51, the maximum value is the 166.51. That is the value of y. In order to obtain the maximum bending stress at this distance, that means the maximum distance happening in the bottom layer. Now we have to find out the bending stress, maximum bending stress. Maximum bending stress comes when y becomes maximum. Sigma maximum comes when y becomes maximum. Alright. Now that's why we consider the maximum y value, that is 166.51. We know m value here. We know the pure bending equation. M by I equal to sigma by y equal to E by R. Now we want, based on the data is obtained such a way that we can use these two relations, M by I equal to sigma by y. So this is the relation we follow. Now we know y maximum, m we know, that is 40 mega Newton millimeter. M value given 40 mega Newton millimeter. That is 40 into 10 power 6 Newton millimeter. Substitute here m equal to 40 into 10 power 6, I value sum of I1 plus I2 plus I3, I1, I2 and I3. That I value is the value 40 into 10 power 6 by I value times Y. What is the 166.51? Then the maximum bending stress obtained here it is 23.377 Newton per square millimeter. So this is the maximum bending stress calculation. That is the third objective achieved. We achieved the third objective. We completed third objective. The first objective is location of neutral axis. Second objective is the moment of inertia about neutral axis. The third objective is maximum bending stress calculation. And one more objective left. The fourth objective here. First objective bar way, second objective neutral axis, third objective bending stress. The fourth objective is the nature of the stress. The nature of the stress can be obtained by seeing the cantilever beam. The load is applied here. When the load is applied, such a way that what will happen? The topmost layer experiences tensile stress, and bottommost layer experiences the compressive stresses. Now the maximum stress obtained here where? At the distance in the bottommost layer. In the bottom layer the maximum stress is observed. We calculated the maximum stress at the bottom layer, not at the top layer. So what is the bottom layer experiencing? The nature of the stress in the bottom layer for this section of the beam is compressive stress. That is the fourth objective. So this is the problem we solved on unsymmetrical section. We considered the unsymmetrical section about x-axis and here. So what we have followed, let me summarize the problem, how to start solving the problem and what are the objectives. The data was given here, it is as shown in figure, the geometry of the unsymmetrical section and also the maximum, what is the bending moment. But these two are the input parameters, but we have to solve four objectives. Number one, that is the location of the neutral axis, that is nothing but the centroid vertical distance, that is bar y. And second objective here it is the moment of inertia about neutral axis, that is INA, and sigma maximum bending stress. And fourth objective is the nature of the stress. So these are the four objectives. So bar y it came from, that is bar y equal to a1 y1 plus a2 y2 plus a3 y3 by a1 plus a2 plus a3. This is the bar y formula. Next, mass moment of inertia. The moment of inertia about the neutral axis, that is I equal to I1 plus I2 plus I3, where I1 is the Ig x1 plus a1 times bar y minus y1 whole square. If you want to write the total I formula, this is the formula Ig x1 plus a1 times bar y minus y1 whole square plus Ig x2 plus a2 times bar y minus y2 whole square plus Ig x3 plus a3 times bar y minus y3 whole square. This term represents I1, this term represents I2, and this the term represents I3. This is the sum. If you substitute Ig x1 bd3 by 12, b1 d1 q by 12, and a1 b1 d1 bar y minus y bar minus y1, Ig x2 b2 d2 q by 12, that is the web portion. I2 related to web portion, I1 related to bottom flange portion, and I3 related to top flange portion. Okay, in this manner we have to calculate this is the total moment of inertia formula direct. If you substitute, you will get it finally the way we have calculated I1, I2, I3 individually. In one step, in one go, we will get it direct area moment of inertia about neutral axis. So the third objective is the maximum stress, the maximum bending stress calculated from the formula of theory of pure bending equation. And finally, nature of stress, from the concept of the pure bending, when bending stress is taking place in the top here, the beam, the considered beam here, it is the cantilever beam. The cantilever beam, we have calculated the bottom layer, the maximum bending stress. So we applied the load. It is such a way that top layers, top fiber experiences tensile stress, and the bottom layers experience compressive stress. Therefore, the nature of the stress in this problem, here it is the compressive nature or compressive stress. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.